right, so what I want to do now is I want to go through and I want to solve a differential equation that's not much worse than the things that we've seen so far, but nonetheless it's going to be one that we can't solve very easily anyways, any other way. So maybe we could use the series method, but I mean, if you prefer the series method, go for it. I doubt anyone really prefers the series method, but anyways, here we are. Here we go. So what I want to do is I want to solve for x. Here x is going to be a function of t. And I want to solve the differential equation t x double prime of t minus 2x prime of t plus t x of t equals 0, subject to the initial condition that x of 0 is 0. I'm not going to give any restrictions about the second derivative of x. Okay. If I gave you, I mean, I could give you a condition on the second derivative, but that's fine. So I'm just giving you one initial condition. This is a second degree equation. That means that we're going to have one constant in our answer, and that's totally fine. So what I want to do is I want to just kind of go through and walk through all the steps. And what we're going to do to start with is take the Laplace transform of both sides. So we're going to take the Laplace transform of both sides. We're going to have the Laplace transform of t x double prime minus 2x prime plus tx, and that's going to be equal to the Laplace transform of 0. And by linearity, what I can do is I can separate this on the left to be the Laplace transform of t times x double prime of t minus 2 times the Laplace transform of x prime of t plus the Laplace transform of t x of t, and that's going to be equal to the Laplace transform of 0, which is 0. Okay. And it turns out that what we're going to need to do is just look at all of our rules that we need. So for t x double prime of t, I think it's worth just kind of going back and forth between all the rules that we know and how this is going to work. So for t, for t times the second derivative, we're looking at rule 23. Okay, and so we're looking at rule 23, and then we're also going to need to know rule 20. Okay, so rule 20 and 23, and then later we'll need some other stuff. We'll come back and we'll look at this table. But by rule 20 and by rule 23, what we're going to have is the following. So we're going to have, let's see, the t times x double prime of t gave us negative s squared times capital X prime of s minus 2s capital X of s. I'm going to draw my capital X's with these kind of annoying little lines at the top and bottom. Okay, so I'm going to draw them with these little lines just so that we know that they're capital X's, they're transforms. So anyway, so we get negative s squared capital X prime minus 2x capital X of s plus little x of 0. Okay, and that was just for the Laplace transform of t times x double prime. Next, we're going to subtract twice the Laplace transform of x prime, and so that is just s capital X minus little x of 0. And then we're going to add to that the Laplace transform of t times x of t. And if we think about t times x of t, that had the formula that was just minus. So if we remember, that was just minus capital X prime of s. And then we want this to be equal to 0. Okay. And then let's cancel out some things. It turns out there's some nice things that'll actually cancel here. Let's see. We look at well, they don't really cancel, I shouldn't say that, but if I look at x of 0 being 0, that means that that term and that term are both 0. And other than that, we're kind of stuck with what we have. So this is going to tell us, let's see, we have negative s squared capital X prime minus capital X prime, and then we have a minus 4s capital X. That's going to be equal to 0. And what I want to do is let's move. We're going to need to solve for capital X so that we can take the inverse transform. We have capital X and capital X prime. That means that we actually need to solve this differential equation for capital X prime. And for capital X, we need to solve that differential equation and find just what's our solution, capital X. So what we're going to do is, let's move. It doesn't really matter how we proceed from here. There's lots of orders, I should say. So let's factor out a minus s squared plus 1 capital X prime of s. And I'm going to move the 4s capital X over to the other side. So it's 4s capital X. And yeah, if I think of this capital X prime as, say, dx ds, this is a separable differential equation. We don't really need to write it as a separable differential equation if we know logarithmic derivatives. So let's just do it this way. So I'm going to divide both sides by capital X. On the right side, I'm going to get negative 4s over s squared plus 1. And notice that the derivative, notice that the left side is nothing more than the derivative of the natural log of capital X. Okay, so that's the derivative. And on the left side, we get negative 4s over s squared plus 1. So integrating both sides means that we're going to have natural log of capital X, and the integral of the right side, so the integral of negative 4s over s squared plus 1 is going to be, negative 2 times the natural log of s squared plus 1. So what I just did mentally there is that you have negative 4s over s squared plus 1 ds. That's negative 2 times the integral of 2s over s squared plus 1 ds. If you were to substitute u as s squared plus 1, you end up with du as 2s ds. That's why I brought out this negative 2, so that you have the 2s ds. And then 1 over u du, it becomes natural log of u. So this is going to end up being negative 2 times the natural log of s squared plus 1, which is what I wrote down here, right? Negative 2 natural log of s squared plus 1. And don't forget the plus c. Okay, that plus c will be important. Remember that our goal is we want to find, really our ultimate goal is we want to find little x of t. But we took the transform, and so that changes our little x's into big x's. So now our goal is to find capital X, and then once we have that, we'll take the inverse Laplace transform. So to solve for capital X, I'm just going to rewrite this one more time, just for ease of following along. This is going to be the natural log of the capital X, and that's going to be equal to negative 2 natural log of s squared plus 1 plus c. And so if we exponentiate both sides, capital X is going to be, we're going to do the usual thing, but let me just write it like this. We'll have e to the negative 2 natural log of s squared plus 1 plus c. So that means that capital X is really, we can write this as e to the c, e to the negative 2 natural log of s squared plus 1. E to the c is, again, just a c. This was negative 2 times the natural log of s squared plus 1. And so e to the c is, again, just another constant. Call it c1 if you like to call it something, just to be consistent. But I'm just going to do what I did in class and just call this, again, another constant c. And then I want to think about what happens to this equation, right? We have e to the negative 2 natural log of s squared plus 1. We can bring the negative 2 up. So that's e to the natural log of s squared plus 1. And e to the natural log of something is just going to be s squared plus 1 to the negative 2. In other words, this is just a constant over s squared plus 1 squared. And we're almost done. So that means that little x of t, let me write this a little bit better, little x of t is going to be the inverse Laplace transform of capital X of s. So in other words, it'll be the inverse Laplace transform of c over s squared plus 1 squared. And now we need to think about what's the inverse Laplace transform of this function. And what we can do is we can bring the c out. So this is c times the inverse Laplace transform of 1 over s squared plus 1 quantity squared. This looks a lot and feels a lot like the Laplace transform of, so this is rule 26, right? 1 over s squared plus k squared squared. It's just that our k is 1. So it turns out that x is just going to end up being this inside argument here where k is 1. So we're going to get, so what I'm saying is that the Laplace transform of this guy, the Laplace transform of 1 over 2k cubed and so on, is this 1 over s squared plus k squared quantity squared. So the inverse Laplace transform of the right side is going to be the left side. So I'm just going to copy down the left side where k is 1. So we end up with, let's see, 1/2 times sine of 1t minus 1t cosine of 1t. And we're done. And the final thing that we can do if we want is we can absorb this 1/2 into the plus c. And so that means that really what we're going to get is we're going to end up with our solution x of t. And it's going to be some constant times sine of t minus t cosine of t. And again, if we did this via the power series method, maybe we would be able to recognize that solution from the series, but maybe not. I mean, certainly we would get a accurate, a correct series solution there, but I think the Laplace transform method really is the easiest way to do this kind of complicated differential equation. Okay, so here's again a problem that we couldn't do any other way, at least not so nicely.